Marhaba. Okay, in this session we want to learn about a new operation on matrices which is called the transpose operation. By operation I mean it's a procedure which takes as an input a matrix and produces another matrix as an output. So for example, addition takes two matrices and produce their sum, and the multiplication of matrices also takes as an input two matrices and produces a third matrix as an output. Now the transpose takes one matrix as an input and produces another matrix as an output. Okay, now let me define it. What is it? The transpose, okay, the transpose of a matrix capital A, let's call it. Suppose we have a matrix A we take it as an input. The transpose of A is the matrix, okay, we denote it by capital A with superscript T, so A transpose. What is this matrix? Is the matrix whose rows are the columns of A, are the columns of A. Okay, so this means to construct A transpose, you take the first column of A and make it the first row of A transpose, and you take the second column of A and make it the second row of A transpose. So let's take a quick example. Now let's suppose that we have a matrix A, and this matrix has two rows, 1, 2, 3, 4, 5, 6. Okay. Now let's compute A transpose. Okay, then what is A transpose? Okay, so you can take the first column, which is 1, 4, and make it the first row here. So here is the first row. Now take the second column and make it the second row in A transpose. So 2, 5 will become the second row. And take the third column in A, 3, 6, and make it the third row. Okay, and it's the same if you want to say take the first row and make it the first column, 1, 2, 3, and take the second row and make it the second column, 4, 5, 6. Okay, so this is A transpose. And notice that if A has dimension 2 by 3, then A transpose has dimension 3 by 2. And second, if you want a formula for A transpose, so if A is denoted by Aij, and say the entry in the ith row and jth column in A is denoted by Aij, and suppose in A transpose we denote the entry by Bij, then you need to see that Bij is equal to Aji. Okay, so for example, what is this entry? This is B. Look, the entries of A transpose are denoted by Bij. So this is B32. You need to check that B32 is equal to A32. What is A32? It's the entry in the third. Sorry, it's not. Now what's B32? B32 is equal to A23. Okay, see, this is what I said. Bij is equal to Aji. So B32 is equal to A23. What's A23? It is the entry in the second row in A. So here is the second row and third column of A. See, this entry is equal to this entry. Now, for example, what is this entry? This is B12. It should be equal to A21. Where is A21? Second row, first column. So 4 and 4 and so on. Okay, now there are matrices in which after you take the transpose of them, you get the same matrix. And these have special name. So definition. Notice that if you take the transpose and you get the same matrix, then this matrix must be a square matrix. So let A be a square matrix, then we call A symmetric. So A is called a symmetric matrix. So this is the definition of today. Symmetric if and only if A is equal to the transpose of itself. So if you start with A and you take the transpose, which means you make the rows columns, then you get the same matrix. Okay? So if this happens, then you call the matrix symmetric. If not, then it's not symmetric. So let's take an example. Let's start with a matrix which is a 3 by 3 matrix, and it's 1, 4, 5, 4, 2, 7, and then 5, 7, 3. Okay, look at this one. So this is the matrix A. Now let's compute A transpose. How do you compute? You take the first row and make it the first column. So here we have 1, 4, 5. Then take the second row and make it the second column. So here we have 4, 2, 7. And now take the third row and make it the third column of A transpose. So 5, 7, and 3. Okay, and see the corresponding entries are equal, and so the matrices are equal. See, here we have 5, 5, 7, 7, 3, 3, and so on. So these two matrices are equal, and so A is symmetric. Okay, clearly the identity matrix is symmetric. Okay, and notice that when we have symmetric, the name comes because we have a symmetry across the main diagonal. Look here, imagine the main diagonal is a mirror, and now we have 4 and its mirror image, 5 and its mirror image, and 7 and its mirror image. Okay, so here we have symmetry. Okay, another example is 1, 2, 3, 2, 1, 4, 3, 4, 0. Okay, this is another 3 by 3 matrix which is symmetric. Either you compute the transpose, or simply you look at the symmetry across the main diagonal. You see here we have 2, 2, 3, 3, and 4, 4. Okay, this is a symmetric matrix as well. Okay, let me finish this session by quickly talking about some properties of addition, multiplication, and transpose. So first, for example, okay, let A, B, C be matrices. Notice that if we add a matrix A plus B, we get the same matrix as adding B plus A. So this means that addition is commutative. Okay, second, if we add A plus the 0 matrix, remember the 0 matrix was the matrix in which all of its entries are zeros, then we get the same matrix. So here I put bold 0. Okay, and notice that to make here we are assuming A and B have the same dimension for addition to be defined. Okay, and the third, notice that addition is associative, which means that if you add A plus B first and then add C, you get the same matrix as adding B plus C first and then you add A. Okay, fourth, so we know that multiplication is not commutative. We've seen an example. Now, but multiplication is associative. So if you multiply A times B first and then by C, you get the same matrix as multiplying B times C first and then by A. Okay, what else? We have the distributive property of multiplication over addition. So if you multiply B plus C by A from the left, then you get A times B plus A times C. And if you multiply it from the right, we also have the distributive property. Why do I say from the left and from the right? Because again, multiplication is not commutative. which means A times B is not necessarily equal to B times A. Okay, so if we multiply from the right, we also get BA plus CA. So this is a theorem. You need to prove it using the multiplication definition, the addition definition, and using our notation of matrices. Okay, here is a statement which you can prove by induction, which says if you have a matrix multiplied with itself m times, and then you multiply it by a matrix, the same matrix multiplied with itself k times, then you get the same matrix multiplied with itself m plus k times. So this is, you prove it by induction on k. So when k is 0, then a to the 0 is the identity, and the identity times any matrix is itself, so we get a to the m, and m plus 0 is m, so we get a to the m. So this is the induction, the base case, and then you prove it you show the induction step. Okay. Now what happens if you take a matrix A and take its transpose, and then take the transpose again, you get the same matrix you started with. So if you start with a matrix, you flip the rows to columns, and then again you flip the rows to columns, you get the first matrix you started with. Second, if you have A plus B and you take the transpose of them, then you get the same matrix as taking A transpose first and then adding it to B transpose. Okay, so transpose distribute over addition. However, it's not the case in multiplication. If you multiply A, B, and then take the transpose of the product, this will be the transpose of B first times the transpose of A. Okay, so again, you need to show all of this. So here you need to use the definition of multiplication and the definition of transpose. And the hint here is that if A is equal to Aij, then A transpose is equal, say, to Bij. And what is the relation where Bij is equal to Aj? Okay. So this means the entry in A transpose, which lies in the ith row and jth column, is equal to the entry in A, which lies in the jth row. Okay, the first number is 4 rows, and the ith column.